Our speaker this afternoon is Nikos Pelekasis from the University of Thessaly in Greece. So Nikos did a PhD at SUNY in Buffalo in the US. That was in chemical engineering. And then a postdoc with Andreas Akrobos at CUNY in New York. And he's now based at, as I said, at the University of Thessaly, which is in Volos in Greece. So one interesting fact about that is it's where Jason and the Argonauts left in Greek mythology on their voyage looking for the Golden Fleece.
Yes.
Okay, and so Nikos is going to talk about computational fluid dynamics and stability of interfacial phenomena.
Well, thanks, Mark. I'd like to thank, the organizers of the program for giving me the opportunity to present our work. Computational fluid dynamics, stability of interfacial phenomena in the presence of acoustic, viscoelastic, adhesive, Lorentz forces. I will not be talking about Lorentz forces today, but if you allow me to indulge myself, the scheduled prepper meeting, I will advertise a second talk this Wednesday at 11 o'clock, if provided there's enough time. I don't think so. There will be time to talk about both these problems. I really appreciate your input in both cases, in both both lines of research. So, in other words, I'm going to be talking about simulations of coated microbubbles, either alone, not in the vicinity of the substrate, subject to acoustic disturbances. These are open flows, and I think I'll be able to talk about the closed flows, where there's a coated microbubble in the tube in a Brotherton type of flow arrangement. This is now a two-phase flow that Archimedes talked about, so I'm not going to be spending any time with that. It's associated with the rest of it in the sense that people use this two-phase flow where there's a surfactant in solution in the liquid phase in order to produce bubbles like this one, coated microbubbles like this one, once the interface is stabilized. Okay, I've been talked about that. I'm not going to be spending any more time. The other thing that I was going to talk, and there's not going to be enough time to do this today, so if you allow me, I'm going to do it on Wednesday at 11 in the morning. This is another issue where there is spreading of the liquid metal in the presence of Lorentz forces. And yes, this is in a totally different context, but a line of work that we've been doing for a long time. I'm going to be talking about that Wednesday. It's also important for us, because, Now, okay, let's start with coated microbubbles. First, we talk about open flows. Now, okay, I think most of you are aware of this. Coated microbubbles, also known as contact agents, they're bubbles diameter on the order of micrometers, surrounded by viscoelastic coating. They use that to protect them from diffusion, protect the gas from diffusion into the vasculature, into the blood flow, because that's what they are used for. They're intravenously injected into the blood circulation, and because of the small size, they can enter into the narrowest capillaries. Two types of materials are used. This is for the coating, polymeric shells and phospholipid shells. Okay, the major technological applications are because bubbles are nonlinear scatterers, so they produce backscatter that distinguishes them from the nearby tissue. So they improve signal, and they improve imaging. Like this is, in this case, this is the carotid artery, this is the blood flow. We have bubbles, there's bubbles injected in the blood flow. These are atheriomatic plaques, asymptomatic atheriomatic plaques. So one can get an idea as to where they are. Plus, I'm going to talk about that today, if microbubbles are found within these plaques, one might get an idea as to what the reason is and what stage that is. It can be quite useful, Okay, recently targeted molecular imaging has been developed where special ligands are attached to the shell to facilitate attachment to specific pathogenic area in order to provide better contrast enhancement in a particular area. Now, once you get them there, then you hit them. Now, you can also use them for drug delivery, because they're drugs that normally they're carried on the shell, which can be modulated accordingly. So if you hit it with a large enough ultrasound, then they break, and the payload or the pharmaceutical payload gets to the pathogenic tissue. Of course, there's a transport process involved here. I'm not going to talk about that, but it is quite useful. Of course, in order to get to the certain part of the vasculature that we're interested in, they have to translate besides pulsating. So we'll talk about the manner by which they translate and how this depends on their deformation. The recent creatures called microswimmers that are, yes, please. By the way, at any point, feel free to
it was very dangerous to have bubbles in our blood.
Yes.
So these are specific bubbles that are not dangerous? Or is it?
They're not. Actually, one of the major concerns at the beginning of this business was that perhaps if the bubbles, or if they get together, there might be a problem because of Ebola and other things. No, it doesn't happen. They're quite small. You don't get that many bubbles in one capillary, right? There's not that many.
And they are not air bubbles, so they could also dissolve as soon as they are not.
Yes. Yes, again, thank you. So these are coated bubbles. If without the coating, they would dissolve and they would disappear. So you want them to survive for at least a certain amount of time until they reach a certain part of our body so that they can do whatever we want them to. That's why they have the coating. Okay? Which is, we prefer a lipid because the lipid coating is easier modulated to do other things as well. So we now want to see also how they translate. We'll talk about that. And drug delivery now, again, there's two issues, there's two ways. You either hit them with a very large amplitude sound disturbance, then they break and they deliver the payload, or it doesn't have to be that they don't have to break. It can be a slightly smaller amplitude. Now, depending on, you want that so that they pulsate and they generate holes in nearby tissue. That's sonoporation. It's been around for a long time. There are two different modes for that. Larger amplitudes, they generate jets. Even this is a tricky issue because if there's coating, the jet, they have bending resistance. They're not going to make intense jets. Most likely, they will break. The coating will break the moment you will have a jet. But in any case, you do get a jet eventually, but it's a free bubble oscillating mainly, and it builds holes in the nearby tissue. For smaller amplitudes, you don't have jets, and you have steady microstreaming, which is a very important phenomenon. People study it for a long time. I don't have to remind anyone about the work by Lorentz or the acoustic microstreaming. It's a very important thing. I'm just going to mention here the work by Nyborg and Jason, where he emphasizes on steady streaming next to the wall. You need that because the shear is, on average, the shear that stretches the tissue to open. Now, Elder published an article a year later where he presents different types of steady streaming patterns, depending on the size of the bubble, on the viscosity, so on and so forth. There's a recent paper by Margot in Nature, 2003, where they talk about steady streaming of coated microbubbles, but this is now, notice, this is on the towards the back of the fluid, it's to the wall, and it's based on the work by Ronnie Higgins, where he predicts microstreaming when there is pulsation and translation when they are out of phase. Okay. In any case, the reason why I'm talking about this is that I haven't seen, what people do work, I haven't really seen simulations capturing that as nicely as I would have. Of course, at any point, feel free to enlighten me, perhaps I'm missing something. Simulation that really capture that convincingly. We've done also some simulations, we're not very happy with them. It's not where we want them to be. But there are experiments. In any case, I think it's an open site, in my opinion. Okay, now, and of course there's wall adhesion. Because you want them to control the motion and kind of dock them, have them kind of adhere next to the substrate and eventually see how they behave in this context. This brings us to the issue of acoustic signature, whether they are here, whether they adhere, whether they are near the wall, whether they're freely circulating in the vasculature. We'd like to be able to say something useful about that. So how the resonance frequency changes. Now we want also, this is, normally it's associated with the breathing wall, with volume pulsation, but they deform. These are an elastic wall, and they deform. When they deform, sometimes this can help the translation. The way they behave, they buckle, that is, they deform. But this is something that we should be aware of, and we can utilize it, understand it, and model it. There's recent work with the locomotion of bioparticles that are employed as drug carriers. Eventually, I think it's one thing that we should decipher, because it's not easy, the interfacial aerology of such particles. I think it's an interesting problem of interfacial aerology, which we have to clarify. Then, mechanism for trapping the bubble near a substrate, how it happens, and understand microstream. Okay? So, let me give you, a short outline of the tools we are using, mostly the very tools. So we studied two different problems. This is the bubble nearby substrate or free. Now, when it's nearby substrate, it's normally spherical. We take it to be spherical, either stress-free or pre-stressed, because this is, remember, this is a gas. It has gas inside. If you keep it for some time, gas diffuses. Not much, but will diffuse. So chances are when you hit them, when you interrogate them with an ultrasound, that they will be pre-stressed. And that bears certain the consequences of that. Okay, we assume asymmetric variations. There are problems where 3D is important, but that's what we assume. Characteristic scales, the radius, the frequency, what we insulate them, velocity, and through that we can get the pressure and velocity. This is another problem that we recently started looking into. Now these are nearly spherical, but they have an imperfection at stress-free conditions. This can be useful because this imperfection, it changes the bifurcation diagram. There is a lockdown effect on the buckling, and then they have several consequences. Okay, now in the surrounding liquid, we treat it as a Newtonian fluid. Okay, we know that the blood may not be Newtonian. It is not Newtonian. As a first step, we assume that it's Newtonian fluid. Continuity, Navier-Stokes kinematic condition. That's pretty much, I'm not saying anything new. The issue that happens at the wall, at the interface between this, the coating and the liquid. Now, the stresses of the liquid side and the gas, there's a difference. Now, it's associated with, mostly with elastic stresses. There might be a little bit of surface tension. What happens if this is an elastic coating? There might be some openings where the gas is in contact with the liquid, so there might be a certain amount of surface tension, but mostly it's elastic stresses. Here we can combine them in one form. It's formally nice. Now see that these are the elastic stresses. It's important, even at this day and age, to be specific as to what we do with the elastic stresses. Now we treat them as a viscoelastic membrane. I have to say that what we do is not like the Pelekasis or the Bonos or the Thessaly model. It's classic cell theory. That is, small thickness, the normal at the base, base state remains normal as it deforms. We assume that the normal strain to the shell is not as important as the membrane strains, and we also account for shear, the transverse shear. Now you can reach this form of the elastic stresses. Either you can go via for example, Levi Simmons, I suppose, Achilles chooses, or you can do what Hale and Hazel that we have been using. Of course, we allow for non-linear constrictive law. That is, the strains would be a bit larger. We don't go with the Hooke's law for always for the strain. But it's pretty much a standard approach. I'm not proposing my own model here. I think it's important to stress that. This is classic circuit. So, but, okay, there's a viscous part as well. This is the viscoelastic. Now, normally, typically, we tend to use the same value for the dilatation of the seal cell viscosity. That's if we don't know to what extent they're different, that's what we're doing, it's okay. In certain cases, I believe that we may have to introduce that. It's not the same. Okay, then we have this is the mass continuity within the gas, the abatic laws, depending on the power of gamma, and we place an acoustic disturbance in the far field. So the wavelength is much larger than the radius, so we simplify it to this form. Okay, numerical. We don't do numerically. We use ability analysis as well. We'll talk a bit about the numerics now. We do calculating finite element methodology. It's a super parametric hybrid scheme because we're dealing with bending resistance, bending stresses. So these go by the fourth order derivative. We cannot go with the classic biquadratic basis function. So we use them for the pressure, the biquadratic basis function, for the velocity biquadratic, for the pressure, the bilinear. This is the continuity and the momentum. Navier-Stokes note that we haven't stopped one step before doing the Gauss divergence to end up with a surface integral. But anyway, now here the kinematic conditions used as an asset. At the interface, the velocities have to be the same, the liquid and the solid. Kinematic conditions used as an essential boundary condition for the velocity. Whereas the first balance equation is used for the calculation of the bubble shape. So this is the form of the force balance. We do time integration with the fully implicit Euler scheme. It has certain nice properties, kind of it dumps a little bit the simulation. Non-linearity, Newton-Raphson method. Linear system equations from dealt with the GMS. This is what we do. Now, the mesh. The mesh is important here. We use two methods. I mean, they're not new. They've been around for a long time, but we find out that they're quite useful. The spine method, where this is now showing the case of the bubble interacting with the solid substrate, or this is a bubble that adheres. This is something ongoing. We haven't fixed yet on the substrate. But as a starting point, we use the spine. What is the spine method? Essentially, we map it to a rectangular geometry where if we know the location of the interface, this is not the bubble that adheres or a bubble that is insulated, then we know the location everywhere. So this is now how we associate R and Z coordinates everywhere in the domain. So if we know what C and eta is, we know what the nodes are, provided we know F1 and F2, which is the RZ components of the shape. Okay? So then we know it everywhere. These are the only two unknowns, the shape of the bubble. This method has the advantage of reduced computation, of course, but it fails in cases where severe interfacial distortions arise. So that is a nice starting point. Elliptic mesh generation scheme. I have to give credit to the line of research starting with Scriven, Christodoulou, Tsimeriotis and Brown, so used with a classmate of mine, Bassaran, and Dimakopoulos and Tsamopoulos. They were using that as well. Now here, what we have, these are now the Euler-Lagrange equations that minimize the functionality that is prescribed. It's not exactly that, but basically here we focus on smoothness and orthogonality. Okay? For the eta and xi curves, we use finite elements. S is the ratio of the along the xi and the eta directions. Yeah, we want them to be nearly perpendicular the interface. This is an arc. It's an empirical parameter between 0 and 1 that controls the smoothness of the mapping relative to the degree of orthogonality. Okay? Now, for the mesh construction, the unknown coordinates of the interface are described by, now the interface by a spline basis, okay, because they have to treat the bending stresses. But what happens is that they are solved along with the velocity field. Once we know them, then they are essential conditions in the problem that calculates the mesh. So in every time step, we apply two different interruption potential procedures. One for the flow of the ship, the other one for the grid. Now the penalty methods that are this pertains to the case of the bubble next to the substrate, the anchors that start, anchors that start at the bubble poles. I have to say that this is it's robust, it's reliable, but it is also an art. You have to, depending on the problem you're doing, you see what parameters are better, but we do mesh refinement and we are happy with what we get at the time. So then give me now we started from this. This is now in the way we started a long time ago, and what gives us the motivation to study this further, I have to admit, is what was reported by the people in 2006, the compression only effect. Why? This is a counterintuitive thing. This is people talking about lipids now. Lipids, they like to be at expansion. It's a strange softening shell. That is, it's like this. They have the peg. If they expand, okay, they become softer. Okay? It's not like the lipid bilayer. This is a monolayer, okay? It's a monolayer because you have water, gas. So there's a hydrophilic and the focal part. It's not like the lipid bilayers that we have in blood cells. It's a different animal, right? So they like to be expansion. So these are simulated. That's why we use the monolithic rock, which allows for some non-linearity in the proceeding. So if you see what they do, well, these are now simulations. There are experiments that verify this. And the resonance frequency now, what is this? These are, okay, now of course this is small. These are at resonance. It just says that if we fix the frequency, which is 1.6 megahertz, these are small, so the resonance frequencies, they are on the order of megahertz. Yes, these are relatively hard cells, but in any case, what we see, if we use the Woodin rock, which is appropriate for monolayers, they spend more time at expansion. Now, but the resonance, this is now the backscatter as a function of radius at stress-free conditions, right? So we hit them, the same frequency, we play, this is, we fix the amplitude of the ultrasound. This is the equilibrium radius at stress-free conditions. And we do such simulations and we see where we get the most of the response. So when epsilon is 1, we get roughly 4.5 as the resonance size. If you increase the amplitude, the resonance size decreases. Now, why is that? Well, first of all, as the size decreases, you get larger. Has a higher resonance frequency at linear conditions. But since what happens is that the resonance frequency reduces as you increase amplitude. Not all cells behave like that. It's because of inertia, added inertia, so they go down or they move towards smaller sizes. The thing is that they like to be at expansion. However, in 2006, the group of Penta showed this. They pulsate mainly, they start with some initial radius, and they pulsate mainly at compression. This is why it's called compression on the effect. As they increase the amplitude of sound, eventually they are again mostly at expansion, and as for intermediate amplitude, it's somewhere in between. So this is counterintuitive for monolayers. You wouldn't have expected that. You would have expected them to be mostly at expansion. So it was interesting. People were trying to understand that. I don't know how many, but there was a model that was quite useful, introduced by Marmonto and other from the group of Penta, which essentially said that as pulsates if it reaches a maximum expansion, it basically has surface tension. At lower, there's liquid shedding and there's no elastic stresses. This is a bit, okay, it is a theory, but it's very specific, very specific. It's not very general. Plus, it didn't always agree with the resonance frequencies and other stuff. So we thought, why don't we do classic shell theory? That is, bending modulus, shear modulus, viscosity, stuff like that. Okay. So first of all, what we do, how do we start when we want to tackle such a problem? Well, we do bifurcation diagrams, of course. That is, this is now when there's no hope, by the way. These are, when you hit them, you don't know that there's in stress-free conditions because they lose gas. So when they lose gas, they're pre-stressed. That means that they buckle earlier than you expected them that they would buckle. This is the case for the bifurcation diagram of a spherical shell as you increase the amplitude of the external overpressure. This is the ratio between the volume at the final state with respect to the original radius. So you see that as you compress them at some point, they buckle, they show, they deform. They basically show these type of symmetric shapes, prolate, oblate. The point is that these are all they evolve in lower volumes because they like have lower energy. In the symmetric shapes, they have the lowest of the normal. But if you do that while they're pre-stressed, epsilon, the threshold for buckle goes even below. So why is this useful? It's useful because in the experiments for compression only, they show things happening made this behavior. They knew that it's buckling, but it happened at very small amplitude, quite small amplitude. That was strange and very fast. It's like 4 or 5 periods. It's very fast. Buckling doesn't happen. It takes some time, right? It doesn't happen so fast and not for such small amplitudes. They reported, and they knew, and we all knew that it's pre-stressed, so that goes down the amplitude for buckling. Okay. So this is kind of showing again, it's a spherical shell, it's pre-stressed. How? It has lost some gas. It's reduced, and you get such shapes. But these shapes, they're all at much lower volume. They evolve towards much lower volumes. They have lower energy. They're preferred. Okay. So that's what we did. We're not the ones who did first bifurcation diagrams with coded bubbles. People have done that before. Right? There's a nice paper from Darmstadt, I think, 2014. They show us. The relation, though, with this, it was not quite clear. Now we want to see to what extent this reflects in the dynamics. So then, we also do parametric stability. Oh, by the way, this is a phase diagram in the absence of the wall. The red line is what is equivalent of the Rayleigh-Taylor stability for conventional bubbles. Okay, beyond that, the bubble loses coherence. The rest of these are thresholds for the onset of parametric shape modes. But in this case, the major parameter is the ratio between the bend resistance and the area dilatation. This is the Poisson ratio, and this is the extent of pre-stress, by the way. So now what we did, many people were a bit, they didn't like that because I'm adding one more parameter. Okay, that's normally you don't want to do that, of course, because it complicates the problem, but we added the ratio between shear and shear viscosity and dilatation. Why? Because you move from volume pulsations to shape pulsations because it was important that they pulsate at different shapes. So there's transfer of energy between the volume and the shape modes. And this is controlled by this ratio, among other things. So we did parametric stability by changing this ratio between shear and dilatation viscosity, fixing the ratio between Kb and T, the bend resistance and area dilatation. These lines, the fixed, of course, these are the buckling thresholds for the first three modes. And this is the parametric stability. When showing this, it plays a role, because where they are located, it plays a role. And we saw that from the simulations. Now, this is the same thing, except that we place the wall. By the way, there's no pre-stress here. Equal, the two viscosities, they are the same. There's He and K, there's area dilatation and bending. This is now the same graph, just that we are doing simulations. So what we get, by the way, well, as the discrepancy between shear and dilatation of viscosity in favor of the latter increases, it reduces the amplitude threshold for parametric shear mode excitation. It makes sense. If there's not much shear viscosity, it's easier to get energy from the boiling pulsation to the shear. It's easier to get those shear modes. And that's what we wanted. This is why we introduced that. But if the amplitude is above that red line, you will lose coherence. Below, we get parametric shape mode. This is the buckling threshold. So if we do simulations, we get this. I think that's good. Okay. So it does it pulsates. Volume pulsations, Bjerknes force is the secondary Bjerknes force. It attracts the bubble to the wall. As it approaches the wall, gradually there's parametric shape mode excitation. We excite them, okay, somewhere here, so that there is parametric shape mode excitation. Normally you get P2 and P3. So it reaches and it performs steady, it starts, the wall performs steady pulsations there. What's happening is that the Bjerknes force is balanced by implication force. Happening between the bubble and the wall. The bubble pulsates around the Reisner static situation. You know, the Reisner is a classic experiment they do in solid mechanics. They want to find statically predict the elasticity of the shell, which they hit it. Now, this Bjerknes force, this equal force from beneath, so essentially pulsates there. Now it's corrected because of surface tension and so on and so forth. So that's what it does. These are pulsations. In this regime, we thought it's easy to get some kind of compression only effect because it's above the buckling, below the loss of coherence limit, but it's quite close. We couldn't get it. So then, of course, we went into the pre-stress situation. Yes.
What is this force that's pushing it towards the
Bjerknes force. The secondary Bjerknes force, it arises because of the scatter pressure. There is this, and it's invisible. It's just from, so the bubble pulsates, it's under pressure. The discrepancy goes back because of scatter. If they are in phase, you may have two bubbles. If they pulsate in phase, they attract each other. If they're out of phase, then they repel. It's known since the early 20th century. It's named after Bjerknes. I think him and his son did work on that. Okay? So the Bjerknes force sends it to the wall. As the wall, there's lubrication pressure. It resists that, so it reaches and it does this. So now, if now there's pre-stress, we can do again the parametric stability. What happens? Well, if it's pre-stressed, both the buckling threshold goes down significantly if we do parametric stability, and then we have also the parametric stability goes a bit further down because remember we're above the buckling threshold. So parametric shape mode remain arises because of the sound, right? It's a means to get. You see, what happens is that there is buckling. Normally, it will take a while for these shapes to be up, to manifest themselves on the shape. But parametric excitation helps you and gets them fast. We're trying to explain why we get these shapes compression only at low amplitudes and relatively fast. So it's a combination of the pre-stress and the fact that you get parametric shape moves that appear. There's a dynamic route to that. Yes, so what we do We construct again phase diagrams for the ratio between the shear and the dilatation of viscosity, the amplitude. We get different modes when they arise, and then we do simulations. So the wall presence gets, the backing threshold gets it lower, similarly for the parametric shape mode excitation. Also, let's do some, so let's show the simulation here. Okay, now we hit them, this regime. Well, in the beginning they perform pulsations, expansion, mainly expansion. At some point, you see modes start growing. You can tell this is now the same modes that emerge. In the beginning, it's only the even modes, so the shape is symmetric. But then, because there's a wall, the wall favors asymmetric modes. Eventually, you get this. But the moment you get this, what was surprising is that they don't keep approaching the wall. What happens is that there's a pressure drag and viscous drag. The pressure drag, because there's the surface is larger, it pushes it upwards. And by the way, if it happens due to parametric shape mode excitation, it will happen relatively early. So what happens is that it will appear in this part, because this is what the highest pressure is. So the concavity will happen away from the wall. The concavity will happen here because you have the high pressures. So backwards you get asymmetric shapes, so then pressure pushes them up. That's what happens. And it's quite important because it beats the Beattness force. It doesn't approach the wall, it goes up. You see, and this is it. This is what we registered. Expansion only, compression only. That kind of shows us that we are in the right direction because this happens early, 5-10 periods of the pulsation. That was strange. That was what was very strange with the experiments. They showed that small amplitudes and very fast backing. It was very fast. So we had to play around with, to understand what's happening, play around with the rheology and the dynamics, how it affects the dynamics. Now here, it may not be shown. Over here, you get P3, the red one. You get the even modes earlier, but then you get as it gets closer to the wall, you excite asymmetric modes, and then you move away. Okay, now if we hit it by the way, before we hit it here, in this part, this is the threshold for parametric shape mode excitation. If the amplitude is below, it's in here, then this is what happens now. You get pulsations like this. Then, what happens? Let me show you. These are simulations. Huh? Wait. What it does, it pulsates. In the beginning, because it doesn't happen as fast, it reaches and tries to do what we observed before, in the absence of pre-stress, flatten shapes. But now, remember there's lubrication pressure here, and it exerts the pressure, and still we're above the backing threshold. So it happens on on a larger time scale, you have to wait. That's why we wanted to be in this regime to get fast those modes, like they did in experiments. If you are way down here, it'll happen, but it will happen later. And we do this. Why? Again, it's an asymmetric shape. Because there's the wall, but it looks downwards. It's like this, the pressure drag. So, that was useful, and we published it recently. And we thought, okay, this is interesting, but then it came to our attention, no, by the way, no. I'm going to talk about also open issues here. The previous one, we humbly think it kind of resolved the compression of the effect, but now here this is not the macro, the steady streaming. So now what we do, we calculate, remember this is the pulsating the wall. So what are we doing? We're calculating, because it's not easy to calculate averages with respect to Lagrangian particles, that is, to include the Stokes drift. So we calculate Eulerian drift, Eulerian streaming. So if we stay fixed at a certain point, and we calculate once we reach the stage where the passes like this, we stay at the fixed point. We determine a distance away from the bubble so that we don't get into this, because this, it goes up and down. We need to be at a point where there's always fluid, and we take averages. Why do we do that? We want to see steady streaming patterns, if possible. We want to see if they are towards the bar, if we see something happening at the wall, because this is the holy grail of this business. You want to have at the wall shear, steady shear, on average. This is now starting. I think we need to better as far as our numerics. We need to do an ALE, simulation studies, alternate Lagrangian Eulerian simulation, which allows you to follow Lagrangian particles. But even this would be useful to complete and see what kind of pattern to get and whether we can get it by the wall. Okay, these are now, by the way, these are averages over, we calculate the stream function, and we take averages over the period pertaining to the force. And this is how it looks like. That's why they don't complete all the way into this part. That's what it is. We haven't seen yet pattern, steady stream pattern that affects the wall. Actually, even Nyberg, if you see the bubble is like this, it goes, I think, with the distance to the 6 power one. It's not easy to get steady streaming. Plus, another thing that I want to point out, that normally in papers in this, people, they have the bubble that approaches the wall, okay? Sorry. What happens, they talk about steady streaming beneath the bubble. But it's not going to happen, in my opinion. Why? Because the steady streaming is an directional square effect, right? Same thing is the time scale over which the bubble approaches the wall. So these theories are very nice. They go back to Nyberg and to actually Lamb, but they assume spherical symmetry. The bubble will not be spherical. By the time, once you establish this, the bubble will be flattened by the wall. It's not going to be spherical, but I don't think it's going to be that useful to use this approach. Because on the same time scale that the steady streaming will emerge, it's the same time scale over which the bubble will reach the wall. So it's not going to be spherical anymore. So I don't really trust some of these theories. Yeah. Yes, when they place the steady streaming underneath the bubble. Now, Longe-Hanning's theory is towards the bulk, maybe a different story when he invokes the issue of phase, different phase. So that's one thing. Now, then came to our attention the fact that bubbles that are coated, they tend to progress in one direction. But they have a coating and they have a certain imperfection. So it wasn't, the theory wasn't, we think it's the same mechanism. So if you do here a bifurcation diagram on this type, this is not stress-free, only it's not spherical. If you do a bifurcation diagram when there is a spherical shape or with this shape, you see it happens much earlier. This is called, NASA people call it the knockdown effect. In the amplitude. George Sabu, who was in the group, who originally observed that, he sent me an email, and he sent us an email, and he mentioned that. Okay, so this is the bifurcation diagram of this guy. What am I showing here? This is static analysis. There is this, and we say P infinity is P static multiplied 1 plus F plus 0.8, and we get this, which is somewhere here. So now, we can, what we did, because we haven't done yet global stability to do the whole thing, we just perturbed this shape from 0.8 to 0.9, and we did dynamics. So eventually it will settle to this shape a bit further up, but there is the response includes the frequency of this guy. So if we do Fourier transform of this is the zeroth mode of the shape. We get the eigenfrequency, which is 0.37 megahertz. This shape also has an eigenfrequency of its own. 2 megahertz. So why am I showing this? Now then what we did, we first did an amplitude sweep to obtain the evolution of speed of translation. That is, we fix the frequency and we change the amplitude. In here we have 1.2, 1.5, and we see that as you get a higher degree of deformation, you get faster translation. And it happens, the speed, it happens always when you get the minimum in the volume, when you get most of the shape modes. So as you increase the amplitude, you get faster and faster. On average, you get kind of a relatively fixed speed of translation. Another thing that's interesting here is that we do a frequency sweep. That is, we fix the amplitude and we play with the frequency. What it does then, we fix the amplitude to 0.8. What we see is this. Remember, we have the 0.4, it pulsates between this shape, the button, and this one, such shapes. So it's 0.37 megahertz and 2 roughly megahertz. And we see what happens with the volume pulsation, but also with the translation. So the maximum with the volume pulsation, there is an F spherical, the one that corresponds to this shape. There is a local maximum in the amplitude of volume pulsation near the deformed shape, but the maximal translation happens when at the difference, let's say 1.5, that is F spherical. The resonance frequency near the spherical shape to the resonance frequency of the asymmetric shape. What happens? These two, they interact. They're there, and they get energy from one to the other. I think this is maximized. These are, again, recent stuff. We have to look into them closer in order to make sure. This is the shape. Now, at max compression and max expansion, when the frequency is 1.5 megahertz. Okay. Now, what we did further is we tried to play with the ratio between the two viscosities and also with the dilatation, area dilatation, and see what happens. Now, if it's larger, the area dilatation, the volume doesn't increase much. It's not that much energy to give to the same modes. It's more intense if you are in small, lighter cells. But if I also change the viscosity ratio, now this C is the viscosity ratio between shear and dilatation. We see that the effect is more intense here. That is, if you make the viscosity, the shear viscosity lower below the viscosity volume pulsations, then you get more energy from volume pulsations to the same modes, and you get more asymmetry, and it happens even faster. So there is a maximum in the translational speed and the maximum in the volume pulsations. How am I doing on time?
Maybe one more minute.
Okay, enough. The other thing that we're doing, again, this is current work. We are studying bubbles that adhere on the substrate. Now, this is static. We increase the, now I'm not showing here, I mentioned we increase the interaction potential. It's an attractive repulsive potential. If you get really close, it repels. If you are a bit far, it attracts. So here we're just calculating shapes that we get. This. Remember, because we assume that it's hydrophilic, this is a coated bubble, it's hydrophilic, the wall, there will be a very narrow film. It's not going to be, it doesn't touch exactly, very narrow film. So this is the shape that we get. I will increase the interaction potential. Again, it's the same as before, the elasticity, what happens, yes, the adiabatic law for the gas, so on and so forth. This is now, again, I'm showing those, I should have shown them before. This is just a Wunderlich law for the cell. It doesn't have to be so. We can go with a hook, with hook slots. Not. Now, and the shapes remind us of what was shown by Seibert and Kolsky. Yeah. Now, they have a contact potential. Now we have an attractive repulsion. It's a bit different, the potential we usually what they're using, but it's even shapes. So what we want to do now is, because of course we're aiming at dynamics, we don't want to resolve what's happening underneath that in the contact region. So we did what we do, we follow Blunt and Davis, who did this analysis for static cells, where but for vesicles, where they incorporate somewhere here, they eliminate the contact region by enforcing the curvature at the contact point based on W, which is the dimensionless interaction potential with respect to bending resistance. Now it's not exactly the same because we have history. These are vesicles, they have resistance to stretching. So we do simulation, we see that there's this discontinuity, and we did complicated asymptotics following Blunt and Davis, and we can neglect, what happens is that we neglect, there's the outer transition and the contact region. We can neglect the transition region with these boundary conditions, connecting the axial stress in the outer region and the contact region. This is for the bending. So sorry, this is for the curvature. And of course, we don't solve the normal force balance in the contact region, because that would only basically give us a distance, the very thin film thickness. We just solve the allocation part, the tangential force balance. So we're solving, we neglect we neglect the transition region, we're solving the outer region, and we have the tangential force balance for static calculations, and this helps us even then in dynamic calculations, because we assume static conditions underneath the contact region, just this joining pressure. So first of all, we just redid the calculations, static calculations with a simplified method. Here now, we just change the interaction potential and the properties. Then we play with the pressure for fixed interaction potential. We get such shapes with dimples, again in the manner shown by Lipovsky and Zeifer, quite similar. We did some stability, and we see that where they reach curvature is zero there. Beyond that stage, there is instability, so on and so forth. Static analysis. This is static. Of course, the reason why we're doing this is we're going to dynamics. Okay? So, dynamic adhesion, continuity, momentum equation, integration by parts. I want to stress, and I'm making use of your goodwill, Mark, and the rest of you. What I'm doing, of course, it's tricky. I don't need to explain this to you, that if it pulsates, you have a moving contact point, and you want to do something, you have to do something here. So what do we do? Of course, this is classic integration by parts. What do we do? Of course, there's no velocity zero. What do we do about this guy? Along the wall, I'm saying. Here, Scriven, he uses Navier's equation. You say we satisfy. We reduce this, we calculate the velocity at the wall in a weak manner. We don't apply, of course, that we know the speed. We use this term at the wall, and we substitute for this the Navier equation, U by epsilon, right? So I think I may need to write. You know that better than me. It's this, let's say, epsilon tau s, right? Speed. So I can eliminate this. Forget about values. It's an order one quantity. This is a part of non-dimensionalization. You do that. You bring this down here. Now, when the stress is order 1, okay, this is a small number always. So this is a huge number. U has to be 0 in order to settle this. If, of course, you approach the contact point, this is becoming huge. But this is very large. So this is there, and you get a value for U. This is how you calculate U in a weak sense. We're not the first one to do that. Scriven. Well, I think actually Navier perhaps. Well, not perhaps Navier. Okay. So that's what we do. We're playing around now with simulations to try and see how it behaves. We did that. We're looking for an acoustic response to step changes in the pressure for a free bubble first as benchmarking. So there's a theory with bubble time integral by Maximov, 2005, for a bubble that fixes the contact angle and then tries to calculate frequencies, resonance frequency. So there's frequencies reported there, depending on the contact angle. When the contact angle is P over 2, it's the same. The resonance frequency of the attached of the adhered bubble and of the free bubble, they are the same. Because essentially, the P that does this, of course, it neglects viscous effects, which are not going to be that important. The volume, but at the wall might be different. So these are calculations that we're doing now. And then here, this is for a regular bubble, no coating. And we'll do the same thing for coated bubbles. And we're trying to identify, see what happens with the resonance frequency. Okay, these are not very, the mesh is not the greatest, okay? This is how, the reason why I'm showing this is a now two-dimensional problem, but because of this approach, we don't have to discretize underneath the cell. It's just, if I go back to the first slides, here, this is it. Up at this point on, that's what we discretize, right? We don't discretize underneath the contact region. Now, why I'm showing all that? Let me just finish, and that's it. One more point I need to make. Why am I doing this now? The reason is I would like to see if we can calculate resonance frequencies, but eventually I would like to do the following. Connect this with a transition from here. Let's say there's no pre-stress. Before I showed the transition from here to here, where there's pre-stress. There's no pre-stress. So far, we haven't introduced interaction potential in our simulations. We've shown that this can be very thin, like 100 nano, I don't know. If you introduce an interaction potential, I would have liked to see how you switch from here to something like this. But now, see, this is lubrication, pressure, and getness. This is, again, if I hit it with the pressure wave, we haven't done that yet. Getness, static, just this joining pressure here. If this is possible, for what conditions, so on and so forth. And it reminds me of the Leidenfrost. That's why I was so kind of excited when I saw the Leidenfrost reports in this conference. I thought there might be a similarity to this transition, this situation to that. And with that, I'd like to thank you for your attention and the opportunity you gave me to present our work.
Thanks, Nikos. Perhaps just one or two quick questions before we finish.
Yeah, I think you're right with the Leidenfrost analogy, because in Leidenfrost there are also this rapid variation of the pressure at the, let's say, when you're at the bottom and then the free surface. And then again, they are also to do something that you have shown, which is asymptotic analysis between the underneath of the drops and then the free surface.
Thank you very much. I think so.
So
That's what we're aiming at. It's new, it's not done yet.
and maybe my other question was about you have shown a lot of bifurcation. Do you aim to have some kind of normal forms or some nonlinear, simplified model for that?
See kind of unfolding or stuff like that.
Yeah, maybe some nonlinear equations, simplified equation like a Rayleigh-Tessel
Okay.
equation. So then you could solve easily for your bubbles.
See, Rayleigh-Tessel requires a spherical.
Yeah,
These are not, these are
decomposition involves.
perhaps. Well, that's why we're here, collect ideas. Yes, Sasha.
I'm about shell model. It seems that inertia of the shell, mass of the shell,
It's
is
not there.
neglected.
It's not there, neglected.
But
Yes.
in terms of the resonance frequencies,
Yes.
you can compare it. Is it okay,
Okay.
with neglecting?
I haven't done I haven't shown you the original numbers. It has to do with the density of the shell as compared with the rest of the properties. Normally, in this business, it's small. The cell density is small. We don't account for wave going around the cell. It's quite small. The inertia is negligible.
We can say that the mass of the shell per unit area is much smaller than
Yes.
added mass of
Yes,
of the-
that's how. Yes,
So
sure.
that's important.
Yes, you're right. That
That
would
would be
be.
seen and okay.
Yes, because with respect to even the mass of the
Yeah, much bigger.
even though it's small, still it's not. Different story if you understand what happens with with the intramural pressure between what happens if you heat with the sun wave the wall of the artery, and that's a different business.
Yeah.
Okay? Because there, of course,
Yeah.
it's a different story. But that,
Okay, let's stop there. Just one quick announcement, which is to remind everyone there's 2 seminars tomorrow. One in the morning at 11, and in the afternoon at 3. I'll send an email with the details. Let's thank you, Nikos again.